I'm Les Atlas, Professor of Electrical Engineering. I'm proud to introduce today's speaker. Today's speaker is also a visiting faculty member at our Department of Electrical Engineering. Not currently, he happens to be at Microsoft Research for 3 months, but he'll be coming back after about 2.5 months. So if you like what he's talking about, feel free to come see him in our department. And that's Ricardo de Queiroz. And Ricardo is a PhD in electrical engineering and was at Rochester Institute of Technology and joined the electrical engineering department at Universidade de Brasilia in 2003. 2010, he became a full professor there. He's very well known in areas such as what he's talking about today in image processing, multimedia signal processing, has won lots of awards and been on organizing committees for lots of well-known conferences. I don't want to spend too much time on the bio because I want to get to this interesting talk. And the title is Free-Viewpoint Visualization for Images and Video. Ricardo.
Thank you, thank you. Thank you. The topic I'm going to talk today is it could be the new trend in video and television and broadcast for the foreseeable future. Before I get into the details, I want to give you a sample of what it is. This is a video that came out of KDDI. KDD is a Japanese company that was in 2010. That's some technology that they have been working for many, many years. Look at this. Actually, it's a soccer stadium. There are players there, and you pretty much can choose where you want to, from which point of view you want to watch the video. You just choose that. So you want to see from behind the goal, you want to see from the top, from the bottom. Of course, this is not this is done offline. This is there's a lot of computer graphics going on. It looks more like a FIFA game, but it's not. It's supposed to be live. One day, that's the whole point. One day we're going to do that live with regular sports event. So in some sense, this is what we are trying to accomplish. Not only here, people at Microsoft, they are working on this, and people in Japan, they're working on this, and even in Brazil, people are working on this. So let's go forward. So we have many camera arrangements. The first one is the concentric. Is the concentric idea. What do I mean by that? There are many cameras pointing to a point. So I have all these cameras. They're concentric oriented, and so that you can move around that object or person. So you can see that person from any sides. Just like was the stadium there. You can watch the football game, the soccer game from any direction you want. I'll give an example here. This is a Voxel demo. This is real time. This is done real time in Microsoft Research. This is not the latest one. So of course, this is not fully synthesized because they don't have time to synthesize the back part. See, that's real time. It have to be captured and transmitted. Capture, transmitted, and display for you on the other side. So this is just a technology called Voxel. There are pretty much two competing ones, the meshes and voxels. And this is just, this is not the latest one that their group at Microsoft are doing. They have newer technology now. Actually, there are two newer technologies over there competing. But anyway, this is another interesting example of what could the future be for that. So the whole idea on this is like, I'm here, I'm talking here, and I want to have that meeting with someone across the world or in another place, another office or whatever. So I can transmit myself over there, and the person can see me from any viewpoint in direction he or she wants. You can also do this parallax thing. Look at this, the impression depth. that you have looking at this. See, it looks like the book is there. It looks like these objects are there in the TV, but they're not. See, the TV is flat. That's just an illusion, and that's caused by, this is my student, Tassio. This was done many, many years ago, maybe 6 years ago or so, or at least. So pretty much what we're doing is that he's just tracking where you are. You're in front of the TV, and it tracks where you are, if you more to the right side or more to the left side, and then displays the right image for you at that moment to give the impression that you have depth. That's called motion parallax. So that's what you do. Now you don't see that, you don't have that sense of depth, just like he has, because the system was adjusted for him. So for that, you have to capture this object from many positions. You have to do the multi-view capture to do the free viewpoint. You have another form, is the eccentric. The eccentric arrangement. In an eccentric arrangement like this, these are 3 examples. The one on the left, this is used by Google for Google Street View. So the one on the middle on the top is the Ladybug. That's a very popular camera from Point Grey, which is one of the most popular camera manufacturers here in the US. I mean, they're cameras for laboratories, more like scientific cameras. And this is, I don't know if you've seen that, this is called Bubble, or Bubbly, I don't know how to call it. Have you ever seen this one? This is like a sphere, a little sphere. They have many cameras. You just toss up. It senses when you toss it up, and when it's on the highest point, it just shoots many, has many shots in all directions, so you have like a panoramic view of your environment. So if you're going to a party or in a park, you want to see everything, just toss it up and get it back. And apparently it's very robust, so even if you drop, that's okay. But when it's up there, it takes pictures from all directions, so you have a 360. Not 360, it's a stereo angle, so a solid angle. So you have it all directions. Anyways, this is a movie I took. This is a recording I did on in my computer. I was using this air panel. Look at this. It's just an airplane going to one of the most beautiful places on Earth, the Cinque Terre in Italy. But then you can go with the mouse, and then you can decide what you want to watch and where. This is what decisions I made before. when I was watching that, I decided, let's turn left, turn right, so I can look up, look down. So here, now I took my mouse. My mouse is quite here. Then I'm going to probably turn right, and then I'm going to drag here. So I want to see that side. I want to see up. I want to see down. This is another example of things where you choose your viewpoint. You see, you're not stuck with the director's point of view. Okay, so or whoever created this. So pretty much you're going there, and I think you get the point of that. So, but the scenes are so beautiful. Monte Rosso is so beautiful that I always enjoy watching that. So in any case, so you can drag, you can watch the bottom, you can watch the sky. It doesn't matter. You choose what you want to watch. So no, let me see. It's just about finished. So there is another possibility. Then you can have another ad hoc arrangement. That's what Professor Huang's here is working with too. It's like, what if you have surveillance cameras? And I put many cameras here, so it's some kind of multi-view too. So I have a camera here, another camera there, and they're taking shots of this environment from any direction. And I give you more examples of his research, the research that's been done in his lab a little bit later. But in any case, so you could, on this surveillance, what does it have to do with Free-Viewpoint? Because with these surveillance cameras, you might be able to synthesize the environment. You can discover the environment here. And then you can view that from any position you want. I want to see that, but I want to see what's going on from that direction. You might be able to do that because you have a camera here, you have another camera there. You can discover objects. You can do assisted driving. You can go on the streets and find, oh, let me turn right. No, you can't turn right because there's a car right there. And you can look at that. So this is the kind of things you can do. Okay, before I go ahead, so let's talk about some of the technologies behind it. So this is the multi-view video. You might hear that if you get interested in this talk, if you get interested in technology, you're going to search for something. You're going to start searching on multi-view. That's where it starts. So in multi-view, you capture a number of frames from different positions from the same scene. So you have an object here, then you have a camera here, another camera here, another camera here, another camera here, and so forth. So you have many cameras pointing to that object if you have that concentric arrangement. So what we want to do, we want to be able to watch that scene from any direction you want. So that's why it's called multi-view. This is, so if you want to flip through this, to the many views of this, this is just 4 or 5 views of that one particular scene called the ballet dancer, which many people use for testing. So this is not very good. It kind of skips through that position. So there's something missing there. This is not, that does not bring too much realism. If you have to skip through the cameras. So we have to do a little bit more than selecting cameras. All this Free-Viewpoint that I'm talking about is not choosing a camera. It's more than that. Because you might have a camera here, I have another camera there, but there's no camera here in between. But yet, I want to see this, I want to capture the scene from this imaginary camera. How do I do it? That's the whole point. So I have to create, I have to interpret. This is called view synthesis. So the synthetic views. You synthesize the views based on existing cameras. And we will talk about that later. So, and even if I do this, let's see if this is. So I can do this, this same, I'm sorry. So you can do that with the video. So the motion, that's the one thing is for you to get a static object and shot from any direction you want. The other thing is to get video, dynamic, real, live material, and then you be able to take shots from any direction and choose which direction you're going to watch all these dynamic scenes. So that scene, it was not a shot taken from many point of views. It was actually a movie shot from any point of view. So all of this follows this, what called the Multiview Plus depth model. What is this? Is this for, it means that for every image, this is called a texture image or color image. This is the image of the scene. You put together with it a depth map. You estimate a depth map. How do you estimate depth? There are many ways. One of them, you can use a Kinect, for example. But if Kinects are not available, or the most common way, you do that visually. Visually, I mean, you have a camera here, you have another camera here. They all look at the same object. So there is a disparity in between this, from this camera to this camera. So this camera observes the object in one position, that camera observes the same object in a different position. From that disparity in between views, you can calculate the depth and can calculate how far is this object from you and what position it is. It's kind of triangulation, you know. That's some stereo matching. But once you do that, once you calculate this depth, once you calculate this depth for every view here, this depth map, what does it mean? It means that, see, dark areas means that the object is very far. Light areas here means the object is very near. That's all there is to it. So you need two images. You have the image of the object or the target themselves, like the people there, and their depth, how far they are. And that's very complex too, because this can cause a lot of problems for you. For example, in that depth map here, you have these borders here. What if the borders are not very accurate? What if you blur the border? What if you blur them for some reason? Like they do compression and you blur the border. What happens? What happens is, the guy up front, the person up front, the foreground here is like a meter away, a meter from you. What if the background is like 5 meters away? If you blur the border between them, you're gonna find something that is in between a meter and 5 meters away. Some 3 meters away. So there is kind of a halo around the person. There is imaginary halo. There is an object that is like a ghost 3 meters away from the camera. That does not exist. So you have to be very careful how you represent this depth, because the depth, a mistake in the depth means that object is in a different position in the room. So anyway, so given that, let's go forward. So given that I have this image and this image from the other view, and I have this depth map and the other depth map, and I have the camera parameters, my job now is to synthesize those views. So I have to synthesize a view here, I synthesize another view there. And of course, I'm not going to teach you how to do that. That takes some time, and then I'm not going to bore you to that. And if you're interested, there are many techniques that can point you to everything. So this demands some a lot of mathematical formulas and all that. I don't think that's the venue for you to teach you how to do this. But just trust me, you can do that. And now look at this. Now it gets much better. I'm interpolating the views in between. Instead of being hopping from camera to camera, now I can smoothly go from one camera to the other. But if you look, the problem that you're not trained to that, but there are a lot of mistakes. It makes a lot of mistakes here on the borders of the, when you do the synthesized view, because it's inherent for that. You're creating an imaginary view, a view that does not exist. So you make a mistake. There's occlusion. There is stuff that you cannot see from one camera or the other, period. That's it. And yet, you can see from the third camera in the middle. And you can resolve that. That's occlusion, and you do in-painting, and you have to do some tricks. Do some tricks to kind of mask that artifact, but artifacts happen. So anyway, but not only can do that with a stationary object, which is not the point, but I can do this for, it'll be like the matrix effect. So you can just have someone dancing, and it can move. Remember, this is not moving because there's no camera moving here at any point. It's not like there's no cameraman that is going around. This is done electronically. This is done computationally. Okay? And that's the whole point. So that when I created this movie, so I chose to move slowly, but I could just go from one side to the other. I can choose, I could pick any point of view I wanted for this scene. I just thought it would be nice to have like this matrix thing to go from one side to the other, but it's a choice. You do whatever you want. That's the whole point. You choose the point of view, your point of view. So how do you represent all this? So as I said, you have this most common, that is the multi-view plus depth model. What does it mean is that I have to send, as I said, I have to send this, I have to send the texture image and the depth image for every camera. Option number 2, I could send a solid model. It's the next generation thing. This is like, if you want to represent an object from many directions, you either send the views from any direction, or you just send the object itself, a mesh representation of the object, like a 3D model of it. And then the decoder might be able to render this object and see, oh, if someone was looking at this object from that direction, what would he or she see? I would see that image. So it renders the image to that person. That's what was done. So this is a competing thing. So it can mean objects. Unless this is, I forgot to bring yours. When I made this model of my head, Les did his too. So I'm going to ask that person to get that. Yours. That was done at Microsoft when I visited. So then going to a more technical part of the talk, but still there are a couple of video sequences to watch. But before that, in terms of compression, how do you compress all that? There are standards for multi-view coding. And I have 2 options. Option number 1, I can encode everything separately. Each view of that, each video is compressed separately in a different channel. Option number 2, I can use this MVCs, the multi-view coding standard that they are just developing. And this complicated graphic might not mean much for most of the audience, but it just say they have these many cameras. Each one of them is not only encoded independently. These IBP frames are all types of frames in a video coder. It could be MPEG, or 80264, or 80265, which is HEVC. All of them use these types of frames. The I frames, the B frames, and the P frames. It depends on how the frames are predicted. That's how the compression is done. Compression is done by predicting frames. There's a new frame that comes in, and I want to transmit it. What I do, I try to predict this frame from the past frames. And there are 3 types of prediction. The I frame, intra-frame, P is the predicted frame, and B, by predicted frame. Regardless of that, the message pretty much that if these sequences here of video from this camera, that camera, are not encoded independently. They have interdependencies. You use one sequence to predict the other. Why? Because the views from cameras that are nearby are very similar. If I have a camera here taping you, the other camera here taping you, they're very similar content. Very similar. So I can use this one here to kind of predict the contents of the other one. So that's why how the MVC standard is based. And the thing I'm working right now is this solid compression. So I have this solid that I'm transmitting to the other side. How do I represent that? There are basically 2 ways. Actually, 3. The mesh compression, I can either compress the mesh, that I'm building a mesh like a lattice to describe the object. Or I can do something called Voxel. The demo I showed you was based on Voxel. And they are excellent. I cannot show you, but they're excellent. Microsoft is preparing something that will be just amazing in real-time Free-Viewpoint video based on meshes, not on voxels, but on meshes. It'll be perfect. You look at that, it'll be amazed. Wow, how can that be done? And you're going to hear from that soon. And the other thing you can do like, you have problems with texture mapping and the compression. So even if I do the mesh, I compress the mesh of the object, you have the surface of the object. See, I'm not like a chicken wire it's not enough for you to do the chicken wire of me here standing and represent to the decoder. You have to give the texture, meaning this is skin, this is like a jacket, this is lack of hair, and this is like shoes, and so it makes a difference. Like it depends on the temperature, how much, if I sweat or not, my forehead can be shiny or not. You see, it's the same object, same thing. Is that shiny or not? So this all have to be represented to the decoder to be accurate. So that's very complicated. That's not trivial. In any case, all this is still experimental. This is all subject to many papers and patents and all that. So this is the real time. One real time is older. This is not the state of the art they have in for. This is Chin. She's getting to this. This is for real time Free-Viewpoint video. So she getting. There are many cameras around this curtain there. Look at the reflex on the TV. You see that she's stationary, but now she's rotating on the screen. So pretty much now they're capturing her on all sides. So this is a little bit distorted because this has to be done in real time. Has to be fast. They probably should need more time to do this. You see, and the other thing, infrared to get hair. It's complicated. To get the depth, the Kinects. The Kinects are not going to get the hair right. That's the whole point. So you get this. It's a little bit deformed, but now the second version of this is much better, much more precise. But remember, this is done in real time. Pretty much you can have this and talk to someone across the world. It's like a telepresence of yourself across the world. And that's what I'm saying. This is the future. May not be like many other technologies that didn't succeed, but it would be very nice if this was the future. And you can have this. This is just techniques they're describing the voxelization. This is not based on meshes. It's based on something called voxels. So. Said all that. I described now all the techniques for free viewpoint video. So I guess now you all understand what I mean and what I'm trying to accomplish here. One idea that came out of this is Free Viewpoint TV, Free Viewpoint broadcast TV. What is the difference between Free Viewpoint video and Free Viewpoint TV? Free Viewpoint video is that I send a video to you. I'm here, send to Professor Huang, he receives that, and then we can talk. Free Viewpoint TV, meaning I go to Husky Stadium, put like 200 cameras there. Tape the whole game. Not tape. And live. I have a live broadcast to millions of users, millions of viewers everywhere. And each viewer can choose where he or she wants to watch the game. You want to watch from behind the goal? You want to watch from the middle? What do you want to? And if you have enough camera, you can watch from the top. I don't know. You can watch from any way you want. That's the whole objective. So this is different. So it has many problems here. So go to Maracanã Stadium and put like hundreds of cameras. Has a World Cup, whatever it is. Put many cameras, and then if the whole problem is that. One of the problems that if each viewer can choose its own viewpoint, and you have millions of people, let's assume that one day it will be broadcast for everyone. So someone has to synthesize those views. You have to synthesize one view per person, unless if the person wants to watch exactly the position of the camera. But what if it doesn't? Well, you have to synthesize the position. So. One thing that we are working with, we are assuming that we have a very slow feedback channel, just to so that I have an idea of how what position is each viewer, from what position is each viewer watching? That's, so with that, we can have an idea of if many, what is the attendance for each camera in my scenario. For that, that's why we would use this feedback channel. But in any case, so that's the whole point. You have like tens or hundreds of cameras. And here I might have thousands or millions of viewers. How do I do that? That's a problem. So the network itself might be a problem, might be complicated. And this is not done at all. So we need help from network people actually to solve many problems here. Because I'm not a network person. So you have these cameras. Are you really going to transmit like 100 cameras to every single person? What if all of this is HD? What if each one of them is like, you spend like 10 megabits per camera? So see, that's not feasible. That's not feasible. So the whole point that we have to be smart on this. So in this network here, you might have to have someone has to estimate the depth. How do you know the depth of each camera, or the depth of the players for each camera? Someone has to do that for you. You either have a huge and gigantic gigantic connects, one per camera, spread all over the stadium, or have like a 3D environment. You discover the 3D environment of the stadium, or you have to estimate based on the cameras themselves. And that can be done in real time, a very powerful computer somewhere over here, right at the entrance of your cloud out of the stadium. So you compress the data out in the stadium, send that, someone will do that, the depth disparity and depth estimation, because this is the one that takes the longest. This is very complex. That's the slow part. So you send that, so you might have people that are connected to your network right at the first network. You can have a secondary network with more people connected there, or you can have a secondary and tertiary network, sub-network with more people connected there. Imagine like you're like your Comcast or something. There's someone broadcasting maybe in a stadium, on Dallas Cowboys Stadium, and then to get your Comcast sub-network at your home, that takes a lot of hops, a lot of going through many networks. So for each viewer here, you might have to do view synthesis. So what I'm saying, the view synthesis might be one per viewer, or you can do that, you can get, what if this network here has more powerful computers than here on this network? So maybe I can do view synthesis for everyone here, right there. On whatever, I have powerful computers to do that for you. And then I stream, I do the view synthesis for you in the cloud, and I stream one video for you. Or to get just one stream instead of getting many streams, just one. So the other thing you can do some kind of transcoding, but that's another story here. In between networks, you can transcode to reduce some bit rates, to make compatible, some rates compatible with your network. But so issues. What issues do they have a Free-Viewpoint television? First, you're not going to stream tens of camera views, maybe 100, a couple hundred camera views to potentially millions of viewers. You have to have consistent quality across views. You have to be careful with those things. And you have latency. You have many other network problems. Someone has to do the real-time, customize the view synthesis. Someone has to synthesize the view for you. And you have to do the real-time depth map generation. You have to generate that on the fly. How are they going to do that? All these are problems. This is none of them is simple. And none of that is solved, by all means. If you want to have any idea, that's a paper right there. That's an article right there. So what we are working on this transmission of Free-Viewpoint television. So we're kind of allocating the camera bit rates. We're trying to route the camera streams, and we're trying to transcode data for this subnetwork. So we are working on these 3 topics right now. And still many things to be done. So the whole point that we're doing is like the attention weighted. And this is a very, there's a lot of discussion about this. So in Free-Viewpoint video, you have all these views. Let's see, from 0 to 7, for example. And you want to watch in position 3.4. So I'm going to synthesize a view for you at position 3.4. What does that mean? I'm going to synthesize a view that is 40% in between 3 and 4, cameras 3 and 4. It's 40% of the way from 3 to 4. But if I have a Free-Viewpoint television, I actually don't have one viewer. I have many viewers. So I have this, on this camera position, I have a distribution that maybe the most popular is the 3.4 position. But maybe there are a lot of people watching other views. So what we are doing, what we call attention-weighted rate allocation, is that we do views with more attention, meaning there's more viewers looking at those views, those cameras. We give more bits to them. The views that have less people watching, we give less bits to them, meaning lower quality. So what we want to minimize is the overall observed distortion. So meaning the distortion that we're trying to account for is the distortion that each viewer observes, experiences. So each viewer experiences a distortion. So I want to minimize the overall thing. So let's see if how long it lasts. How long? Another 10 minutes. 9 minutes. Okay. So this is all done by doing some overall bit rate allocation, and I don't want to get into details. I promise not get many formulas. And the whole point is that I have the rate I have is fixed. Because there's a cable that's that thick that comes out of the stadium, Husky Stadium. There's a cable that can't go beyond that. And you have to allocate to all these cameras. So I'm option number 1. I give the same bit rate for all cameras. Option number 2, start doing the attention-weighted thing. So I have to make choices because the sum is fixed. And I want to minimize the total observed distortion. So actually, if I minimize distortion, I have to increase rate. If I want to decrease rate, I'm going to increase my distortion. Distortion is the opposite of quality. Large distortion, lower quality, and vice versa. So you always get something like this. Rate plus lambda distortion is a Lagrangian minimization. So you cannot have both. So you have to kind of choose which one you want, and you have to have some kind of balance between them. I'm not going to get to that detail of the observed view synthesis. I just want to highlight one thing. See, never mind the slide here. I have 2 cameras here. I have a camera on the left side, camera on the right side, and you asked me to synthesize a view for you here. What if I compress the view on the left side and compress the view on the right side and the left side? They're both compressed. They have distortion. So the view you're going to experience here in the middle has some distortion caused by the compression, by the distortion in each camera. So the distortion that you observe is proportional to the distance to the synthesized viewpoint. Meaning, if you want to synthesize a point of view that is very close to a camera, that camera is much more important than the other camera. You know, so a camera here, camera the other side. So if you want to synthesize something very close to this camera is more important than this one. On the other hand, if you're going to do depth, so if your depth maps, if you start compressing depth maps and start giving them problems, so you have problem disparity, then it does not matter where you are here. Any depth problem affects equally whatever you are in the position, whatever you are synthesizing here in range. So pretty much the average distortion caused by depth in a synthesized view is the average of distortions of the depth in each one of the cameras, independent of position. So let me, before, I don't want to, so we have very interesting results here, but in all of them, you always end up trying to minimize some rate and distortion measure. Rate is the number of bits, distortion is the observed distortion. And what we did that was interesting is that we kind of related the distortion of observed by the viewers to the distortion produced by the camera. D, capital D, N, sub N, is distortion of each camera itself. And these gammas here are just parameters that tell how many people are somehow using that camera for their view synthesis, and how much influence does that distortion have on their synthetic view. So of course this takes time to describe all that. So I just want to give you some simple results before I go to my last experiment, last scenario here. So we're doing compression here with 8.264, and doing the view synthesis. The view synthesis program, if you want to play with this, is the MPEG view synthesis reference software. You can get that. You can download those. If anyone of you want to play with this, then you can have you can give two images. You can download the multi-view sequences. And you can start interpolating between them using this. So anyway, so this is just to show some results very quick. But pretty much this is distribution of attention. See, this I have like 9 cameras, and this is a distribution of attention that the viewers have in a simulation. The distribution of attention that each viewer has, the viewers have for each camera. And then if you take that into account, this is a graphic that is very popular for people that do compression. What does it mean? This is bit rate. This is how many bits I spend to encode the camera or encode the video. And this is what? The PSNR here. This is the quality. It's the inverse of distortion. It's a measure of quality. Okay? When the distortion goes down, PSNR goes up. It's peak signal to noise ratio. Okay, so it's the opposite. But anyway, this slide just shows you that the blue curve here is much better than the red curve. The blue curve is the optimal rate allocation that we developed, and the red dashed curve is that uniform distribution, which would be the case if you give the same number of bits for every camera. Just give the same number of bits out of the Husky Stadium to every camera, and the other one, you start distributing that to the cameras that are more watched by people should receive more bits. And I have a similar result with several variations. This is distribution of viewers. I have like 60 cameras here, and I have a number of viewers. I don't know, 300 viewers. And have distribution. So we always can do better if we do the optimization. And I don't want to go to all of them so in the detail, but pretty much the blue curve is always better than the red dashed for any distribution. I just kind of rushing through this because I want to do a quick thing for the end. Is the surveillance network. That's 3 minutes. Okay. This is stuff that's been done Professor Huang's laboratory here. So actually, this slide was produced by one of his students. And pretty much then surveillance network have this wireless network and have these cameras all over the place. And all these cameras here are actually viewing a part of the scene, a part of the street, of the environment. And you want to to discover that environment. Do some kind of environment discovery. You want to understand what it is. And at some point, you want to be able to see anything here for any position based on all these cameras. So you have this. Some of them are mobile camera systems. So all of them share the same wireless network. or at least the same wireless bandwidth. So the whole question, I'm just going to show you just one quick movie here made by one of Professor Huang's students. That's pretty much, these are the videos here on the left side. This is this building here, outside of this building. And this is, you just plug that into Google Street View. You see, but you see here, there are people here in the Google Street View. These people here walking the Street View. Of course, there's this big stone here in the middle of because Street View did not understand correctly that. You know what I mean? So pretty much you have cars. They're just putting cars and people, all the targets within the Street View. That's crude, still crude, but this is very fundamental. This is very cool. Because that gives you a possibility. This is just an embryonic, just like a fundamental seed for something that is going to be perhaps our future of surveillance. Surveillance and discovery of environments. Maybe the whole digital cities might be like this. Again, so the cameras compete for the same bandwidth. So we have multiple targets to track. And of course, the total bit rate is limited because everybody shares the same bandwidth. So the only thing we did was we just came up with this new, we're still working on this. We're still working here. We just have this minimize this, divide the distortion. The distortion I have, instead of being distortion of the camera, distortion the number of false negatives and false positives of the identification of each camera. That's what we're trying to minimize. And so we develop, if you have interest, come talk to me. I can give all the details. I'll not be able to give you more. But again, everything is like this. Is a Lagrangian cost function. You want to minimize the rate. You want to minimize the number of false negatives and false positives at the same time. So you have to choose which one you're going to do. You have to reach a balance between them. So this is, we have to estimate the misdetection, meaning how much this is work in progress, pretty much. What is done is that this is the area of a person in one of those videos there. What's the area of the person in pixels? How many pixels are there in the area of the person? And then here is like the quantizer parameter, how much more compression I have. When you go here, you have more compression. And this is what? The accuracy of your tracking. So the more you compress, the less accurate is your tracking. Because, of course, at some point, it's going to be everything blurry. You won't be able to identify targets. And if the images are very small, the targets are very small, you might be able not to, because they are very far away. You won't be able to recognize that as a person, and not be able to recognize faces and these things. So pretty much you have based on that, we are developing a framework here to optimize the transmission of these cameras to minimize both your rate, minimize the rate for each camera, but at the same time optimizing our accuracy of tracking. Okay, so I think I'm about time, so I just leave you here, and I'm ready to take questions if you have them.
Thank you.
Thank you.
Time for questions.
Give them
Any questions?
I'm pretty sure you have questions. Come on. Have you ever seen anything like that? So
in the demo from Microsoft Research, they use the mesh to represent the...
No, that's a voxel.
The voxel. So I noticed there are some errors, so could you please explain what the error comes from?
Oh, real time. You see, this is not done and redone. This was done all in real time. So it makes mistakes. We have all these cameras. All these cameras have to, that's last year. So I have to look at last year, put cameras and sensors, and have to figure out his 3D volume here. The difference between a voxel and a mesh is kind of a graph. They have these nodes you connect by triangles they're connecting. And voxels are pretty much a 3D volume where they just kind of paint the border of the volume. Imagine a 3D grid. Like you have X, Y, and Z. And then you paint the boundaries of your object. That's the voxels are. Voxels like vortex elements, like pixels. The equivalent of pixels, but in 3D. And meshes are more like a graph. So you have a node connect to that node. But they're different and competing approaches to do the same thing. And so which one's better? Depends on who you ask. People that do voxels think are better. People that do meshes think are better.
Isn't graphics hardware more aligned with meshes than voxels?
Yes.
Or am I? Okay.
Yes, but the people that are doing, some people that are doing it, like Charles Loop.
Okay.
You know Charles. So Charles is voxel. He likes voxel. He thinks that's the way to do real time. The problem that you have to do real time, you have to do fast. If you can do offline, maybe you can do meshes, but you see, graphs are more complicated because you don't have any orientation. You don't know who your neighbors are. You have to look on a list to see who your neighbors are. You know what I mean? So how do you represent a mesh in 3D? It's like a list, like a graph. I don't know if you if you're familiar with graphs, like graph theory. You have to represent a graph.
Okay. Any other questions?
I'm just curious. This H264 Multiview have been finalized around 2009. But so far, we didn't see any kind of smart TV that have that capability. It's already 6 years after the standard finalized.
Well, one thing that I can gather on that is that, well, there is no appealing technology behind it. You don't have content generation that is good enough. You don't have even view synthesis that is good enough in real time to do that. Because all these experiments, all these people do, have a line of cameras here. This is not good enough. So that's why people, Microsoft, and other places are trying to do the solid model. See if they're more appealing, so you can see from more direct. Because if you just have a line and you can just go do this, maybe that's not, you're not going to pay much more just to see you on the line. And all the experiments are just not, I don't think it's mature enough. They're waiting for that to mature, to have more applications, better technology. How about, I have a camera here, ad hoc cameras. I put a camera here, here, here. In the end, I want to discover everything. I want to have Free-Viewpoint everywhere. They can do that. They can't do that. They don't know how to do that. You know?
Other questions? Well, if not, let's thank our speaker.
Thank you. Thank you. Thank you. Thanks for inviting me.